In this one, let's reverse the order of integration. The integral from 0 to 2, the integral from y squared to 4, y cosine x squared dx dy. So this would be very difficult to integrate with respect to x first, because there is no antiderivative for the cosine of x squared. Yeah, well, I mean, you could use Taylor series if you wanted, but to estimate it, but no? Why not? So that's one motivation for switching the order of integration. All right, let's draw the region R that we're integrating over. So we draw the region of integration. We get the limits or the boundaries of R, our region of integration, by looking at what x and y lie between according to the limits of integration on the integral. So what does x lie between? Y squared and 4, and y lies between? And 0 and 2. And then we look at the equal part of the inequalities, right? To get the boundaries. X equals y squared, what does that look like? A line?
Sideways parabola.
Yeah, parabola. I know you knew that. Yeah, the sideways opening parabola, it'll go through 1, 1, 1, negative 1, some other points as well, right? It'll go through, oh, actually, if we put in the line x equals 4, I think that'll be helpful. So if y equals 2, don't you get out to x equals 4 as well? Yeah, and then it goes through the origin. So I think all those points will be on the graph. And then we also kind of got x equals 4, that is, for the ride there. And so it looks like that's going to complete our boundary, isn't it? Oh, except I'm drawing too much, aren't I? Yeah. I just noticed that. That's okay. We're not actually looking at that whole interior, are we? Because y is only going from 0 to 2, which gives me what part of that? Top part. So there's your region R. So if you look at the given differential order, what would be the appropriate rectangle, representative rectangle to draw on there? For the given, yeah, for the given integral, they use this as a model, the horizontal rectangle as a model as to how to get the limits of integration. So if that's the case, then they had to use, for the left-hand function, the left-hand end of that horizontal representative rectangle, that would have been the x equals y squared, and then the right end would be the constant x equals 4. That's if you're setting, we're kind of working backwards, that's if you're setting it up dx dy order, right? But of course we want to reverse that, and now we're prepared to do that. We're prepared to do just that. So what should I throw in my picture then? A vertical rectangle, yes. So is that showing up? Is that yellow showing up okay? All right, so how do you write the function that gives the top part of the rectangle? So square root, you mean?
Yes.
So we want y in terms of x when we have vertical rectangles, right? The usual, what we're used to. And it would be the positive square root, wouldn't it? Right? Everybody, because we're going dy dx order now, right? So y in terms of x, and then I think we're pretty much good to go. So let's set it up. Here's kind of a template. The integrand doesn't change, does it? But now it's going to be dy dx. So now looking at the top and bottom of that rectangle, yellow rectangle, what do we get for the inner lower limit of integration?
0 to radical x.
0, and then radical x is the upper. And then what does x run from? 0 to 4. There you go. So basically, you just want to take apart what you're given and think about what you did, whoever set this up, what they did to get that, right? And then put in the appropriate representative rectangle, reverse the differentials, and of course you have to, if necessary, solve for the other variable, right? If it was originally x in terms of y, you got to get y in terms of x. If it were y in terms of x, you got to get x in terms of y and think horizontally in that case.